Okay, so in this lecture, we are going to study contour integration, a residue theorem. So let's start by where we left off in the 24th lecture, which was to say, I want to evaluate this integral in a closed loop, and this was a Cauchy's integral formula. So this was Cauchy's integral formula. And the condition was, of course, that Fz has to be analytical. Fz is analytical within and along the contour. And I got this result. Now I'll just rewrite my Cauchy's integral formula as this guy, and we wrote it in a particularly useful way, which was to say we just wrote it as a dummy variable of integral, where the integral is over this variable chi, and we wrote it like this. And the usefulness is now I can take the derivatives. So this becomes so on and so forth. I'll just take uh, the nth derivative was this is the contour. Okay. Now this is the evaluation of the nth derivative in terms of the contour integral. So that helps me to expand Fz around Z0 in a Taylor series. This guy. And which I can be writing as this is equivalent to this guy, where an is this guy. So thus you see that we can write a Taylor series, and of course the convergence of the Taylor series is going to depend upon this integral and the choice of the contour. But let's go along. So now what do we do? So now let's say, so I think this is all a recap from the last lecture, but still it's kind of useful. So now let's say the function fz has a pole of order P. So I can write a function gz as fz z minus z0 to the power of P, and this function is going to be analytic. As we saw that limit z goes to z0, fz z minus z0 P was finite. So I can always write, we can write Taylor series of for gz, and that is to be gz is equals to bn to the power of n, which is nothing but b0 plus b1 so on and so forth. And from this relation, fz can be written as a minus p z minus z0 p plus a minus p plus 1 z minus z0 p minus 1 so on and so forth. And certainly, as we shall see, A's and B's are related because G and F are related. So from this guy, I already know the coefficients Bn is nothing but the nth derivative of G evaluated at Z0 over n factorial, which according to the above analysis and my formula for contour integration is nothing but so by the way, this is called as a Laurent series, which is the expansion around Z0 of a function which actually has a pole. So Bn was this guy, and An, as you can see, is related to Bn by An is Bn plus P. Remember, A, B was related to this guy, B1 was related to this guy, because I divide this by Z minus Z0 to the power of P, I'll get this guy. So, which is nothing but n plus p plus 1, and plugging the relation between fz and gz, this guy is going to be fz dz divided by z minus z0 n plus 1. This is valid for n less than 0 as well as n greater than or equals to 0, as we've already seen. So this was the Taylor series and the Laurent series of the function expanded, and now comes a definition. See, we have these coefficients a n. The coefficient a minus 1 is called the residue. So that is just a definition. I expand Fz and this coefficient a minus 1, that is going to be called as the residue. So this would be so on and so forth. So let's see a few examples of evaluating the Lorentz series and also calculating the residue. Once we have the Lorentz series, when we just need to find the power of uh, or the coefficient, this guy, that's going to be the residue. So see, let's see. So example. So let's say Fz was 1 over z minus 2 the whole cube. So now if you can see, this guy has a pole of order p equals to 1 order at z equals to 0, and it also has a pole of order 3 at z equals to 2. Now let us see at z equals to 0. Let us look at z equals to 0. I have this guy as this guy, and I'll just massage it and write it in terms of 8z z by 2 minus 1 the whole cube, and that's nothing but minus 1 over 8z 1 minus z by 2 to the power of cube. And now I expand this, the denominator, using a binomial expansion, and I get 1 over 8z 1 plus minus 3 minus 1 by 2, so on and so forth. And that's going to give me minus 1 over 8z minus 3 by 16 plus 3 by 16z, so on and so forth. So the expansion around z equals to 0 yielded this thing, and now you can see what's the coefficient of a minus 1, or the power of z to the minus 1. That is this guy. So the residue is minus 1 over 8, the coefficient over here. So residue is nothing but residue at z equals to 0 is minus 1 over 8. So all you need to do is to expand it using some means in a Lorentz series and calculating the coefficient over here. Let's see what happens to the pole at z equals to 2. So what I'll do is I'll put a variable as minus z minus 2. So then my function becomes this guy, which is nothing but this was 2. To 1 over 2, Again, I expand in whatever ways using the binomial series. So on and so forth. And I can see that this expansion, the coefficient of a minus 1 is 1 over 8. So the residue of fz at z0 equals to 2 is equals to 1 over 8. In general, the expression for residue is given by this formula, derivative of this guy. So that's the expression for the residue, and for m equals to 1. So here m is the order of the pole. So for m equals to 1, this formula reduces to this guy. Okay, so this was about the residues. It's about expressing in terms of the Laurent series and finding the coefficient a minus 1. That is all to residues. So this was crucial for us to define what do we mean by, or define or build up the residue theorem. So in this lecture, I'm just going to state the residue theorem. We are going to see the proof and the applications of it in the next lecture. So we will just state this theorem and take it up in more detail in the next lecture. So if Fz has a pole, that's the residue theorem. If Fz has a pole of mth order at z equals to z0, and let's say this was the pole and I have a contour over here. Yeah, sorry. So if I have a contour over here, and of course we'll have a Laurent series minus m would be the extrememost term of the Laurent series, and all the plus all the other terms. So it would start with minus m something plus, and then it would have all the positive terms. so on and so forth. So that's my uh, the Lorentz series, so on and so forth. So I am doing a contour integration where I have the single pole of order m, and that is, the single pole is within the contour. So consider the integral. Consider the integral I equals to fz dz. The value of this integral is nothing but 2 pi iota and the coefficient a minus 1, or nothing but the residue. So that is just, that's my, in essence, the residue theorem. So it is nothing but 2 pi iota r c0, where this guy is the residue, nothing but the coefficient of this guy, residue. So this was for a single pole, but this can be extended. So for more than one pole, well, consider the contour with many poles, z1, z2, z3, and that's going to be 2 pi iota and sum of all the residues associated with the poles. The pole can be of any order. We need to calculate the residue of the Lorentz series associated with the expansion at that particular pole, and all add up the poles, and the integral is going to be this guy, as long as this contour encloses whatever poles it has to. So this is the residue theorem, and we are going to see the applications and maybe the proof of it in the next lecture. Thank you.